Welcome to the Composite Laminate Testing Q&A session. Thank you so much for being here. I'm Nick Erickson, your host for this webinar. Ian McIntaggart is joining me today for his second appearance in our new weekly webinar series. His first webinar was also on composite laminate testing. A lot of the feedback we got from that session was that many people wanted more time to ask Ian questions. And since Ian loves talking about composites, he quickly volunteered to jump in and field some questions. So here we are. Just to provide a bit of background on Ian, he lives in the UK. He has over 40 years of experience in the materials testing world, specializing in composites. He's also the chair of the UK Composite Standard Committee and a member of various ISO committees. We're also joined by Matt Spirett, a member of Instron's High Force Applications team, which works closely with customers that test various metals and composites. Now that you know who we are, I just want to provide a quick rundown of how this will work today. Ian is first going to address some of the questions that we received when you registered. He's got a few slides to help with those. And while Ian is covering those slides, Matt's going to keep an eye on questions that come in related to the topic Ian is discussing. So be sure to send in questions as we go along. Finally, once Ian has covered a group of the pre-submitted questions, he'll move on to take some questions from the audience that come in today. Last note, we are slated for about a half hour, but we'll likely go over. Due to the volume of questions we received, we unfortunately won't be able to address all of them live today, but we do plan to follow up after. If everyone's ready, I'm going to turn things over to Ian.
Okay, thanks very much, Nick, and hello to everyone out there. Welcome to the Q&A session on composites laminates testing. So we have had a lot of questions. Here are all the questions we had running up to this from questions from the previous webinar and questions from people registering for this webinar. As Nick said, we're not going to be able to get through every one of these. We'll get through a group of questions. Feel free to add your own questions as we go through the presentation. And we'll be following up on all of these questions later. So here are the questions that we've selected for today. I'll talk about measuring materials properties on tube specimens, talk about laminate testing and flat laminate rectangular specimens, ways to obtain the right failure modes. Look at fatigue testing, important issues with fatigue testing, biaxial testing, ballpoint bend testing on composites, composite rods, measuring strain on components during testing, recommendations for tensile lat shear testing, and some have a little bit to say about hot wet conditioning of and general conditioning of composite test coupons. So let's kick off with techniques for measuring modulus on tube specimens. Maybe it's a little bit more general than just modulus because it's going to cover strength as well. So looking at testing of composite tubes, the biggest issue is gripping of the tubes. So it's necessary to have an accurately machined specimen end of the specimen. Normally the as manufactured ends of the specimen that you want to grip are not going to be regular enough to get good gripping. So they need to be machined. They're probably going to need to be plugged. You see a picture there of a tube specimen with an aluminium plug to go inside the specimen. And then gripped with a collet grip. Now the collet grip has a relatively small range of diameters that it can cope with, but it gives you a very high degree of contact between the grip surface and the specimen. So the introduction of the load by shear is effective. And that kind of grip head can be fitted to a grip driver with different interchangeable heads, so you can test different types of specimens. If we're looking at modulus for tubes, then axial modulus, obviously need an axial test machine, and then strain measurement in the form of either an extensometer or strain gauges. And as for most composites testing, the recommendation will be to use an averaging extensometer to measure strain on both sides of the specimen, take the average to compensate for any bending effects. Then if you want to do torsion testing is going to require obviously a torsion machine. Here's an example of a dynamic torsion machine shown here. It's actually a tension torsion machine, so it's capable of both tension and torsion and combined tension torsion operation. And again, needing to measure the strain is probably done with pairs of strain gauges configured to pick up shear strain.
Hi Ian, we had a question regarding the end plugs on the tube specimens. Are these often removed after the test and reused, or are they considered a consumable?
Well, I guess a little bit somewhere in between the two, Matt. Normally the plugs will normally last for several tests, but eventually they're probably going to get some wear and tear, and they would need to be replaced. But I think you get a good number of tests before you have to replace the plugs. Okay.
Thank you.
Okay. Next question was, is there a way to force a failure inside the gauge section of a tension coupon without having to adjust the gripping pressure and the tabs? Well, obviously the background to this is looking at thermoset matrix specimens, standard specimen types, for all of the rectangular constant cross section. They have bonded tabs generally in order to prevent damage from jaw faces causing premature failures. But of course, with this kind of specimen, and really dog bone specimens are not possible because of potential shear failures, there isn't a preferred failure location. So I think it's a very common experience that these specimens fail in the tabs or in the jaws and not failing in the center of the specimen. And I think this is just really almost inevitable in this kind of specimen design. So in terms of what's happening out there in the world, and something that might be a solution to this in the future, is certainly within the thermoplastic composite community. There's a lot of concern about testing with specimens, rectangular specimens and tab specimens. They would like to move away from tabs because tabs are difficult to bond to thermoplastic matrix materials. Think of polypropylene as a matrix. It's very hard to bond to, for instance. Also, the expense and time of tabbing specimens is really not something that people in high volume industries like automotive want to get involved in. So there has recently been some work in Japan and Germany on producing very gently wasted specimens, as you see in the illustration at the bottom of this slide, where it is a very gradual sort of, not a gross dog bone shape, but a rather gradual taper, but it does give a preferred failure location. And also these specimens coupled with high friction, smooth, but high friction jaw faces, like tungsten carbide coated jaw faces, which can grip the material without damaging it, seems to provide an effective solution. And that will be probably incorporated into the next revision of ISO 527 parts 4 and 5, which are the composite sections of ISO 527.
Hi Ian, sorry, we have some more questions coming.
No problem.
So one of them was, I'll ask you two. Would load string alignment affect the failure location? And also, how would you machine the slight taper of the specimens?
Okay. Well, I mean, that is a good point. I mean, machine misalignment, which will create bending stresses, will create stress concentrations, and depending on the type of the bending, I mean, that could actually be in the center of the specimen, could well be in the center of the specimen. And hence that's actually going to cause you to get failure in the right place. But of course, it will be failure at the wrong stress level because of the bending. So, so the answer is yes, but I don't think it's a desirable thing. I think you need to have good alignment and have this kind of thing. The other part of the question about machining these specimens is that, yeah, modern machining centers are capable of doing these large radius curves and things without too much difficulty. But yeah, you definitely, you need a machine with that kind of capability. Okay.
Great, thanks, Ian.
Okay, moving from tensile static properties to fatigue testing. In fatigue testing of composites, what criteria must be considered before starting a fatigue test or a cyclic test? So first thing is accurate adjustment of the machine control loop, loop tuning. If the machine isn't tuned correctly, you won't be getting the stress levels or the strain levels that you expect for your test. And that kind of thing is made much easier by using automatic loop tuning tools rather than manual loop tuning. And that's something that we feature on our dynamic controllers and software, is a stiffness-based automatic loop tuning algorithm. And there was actually a webinar on this last week, I think. So we'll be publishing a link to that, or there's a link on our website. Then back to the alignment question again. We need accurate alignment, particularly control of bending in compression. Generally, that's going to be done in one of two ways, either using a short unsupported gauge section to prevent oiler buckling, or using some form of anti-buckling guides to actually prevent the specimen. You see the two extremes in these in the pictures on the slide now. So you've got the short unsupported gauge section where the geometry of the test piece will prevent it buckling the dimensions, or you can have a long specimen, or relatively long thin specimen, and then surround that by some kind of guide to prevent it buckling. Although the anti-buckling can be problematic in terms of fretting, might need things like PTFE coatings to reduce friction. Next thing to consider is the test frequency. Testing these polymeric materials, they will heat up at relatively low frequencies in areas of high stress and strain. And you can see that in the illustration there of an open hole specimen subject to cyclic loading. And you can see the heating around the hole there, and with the infrared images. So one of the things that we've introduced recently, or the last few years, is specimen self-heating control. This is an algorithm to control the frequency, and it will modulate the frequency, reduce the frequency to limit the heat of specimen self-heating. The advantage of this is that rather than choosing one safe frequency, which has to work for all stress levels, you will have an optimized frequency at each stress level, and that will improve the overall test efficiency and increase the machine utilization, as you can see in the table, where a 55-day test time was reduced to 40 days, which is significant. And then finally, final point with fatigue testing, or final major point, is choosing the appropriate failure criteria. Are you looking at a stiffness-based failure criteria, or are you looking at something else? Are you looking at matrix damage, which might not be apparent? You're looking at infrared signatures, things like that. So I'd say those are the four criteria for conducting the fatigue test on a composite material. Okay. Biaxial testing. So this question was specifically mentioned fixtures. Really, I think biaxial testing is more a question of actually the machine. We have a range of biaxial testing machines, from electromechanical static machines capable of forces up to 50 kilonewtons, 20 Newton meter torque, probably more targeted at component and device testing than actual materials testing. Then moving up through on the dynamic side, our electropulse range of electrodynamic machines requiring no oil, forces of up to 10 kilonewtons, torques of up to 100 Newton meters. Also smaller capacities, 3 kilonewtons, small capacity. Then going up through larger servo-hydraulic equipment, 250 kilonewton axial force, 2 kilonewton meters torque, largish machines. And then finally, going away from tension torsion and looking at cruciform biaxial machines. There you see a typical cruciform specimen. So here we're looking at orthogonal stresses and strains. And typically, a machine like that is composed of 4 actuators. You can see the machine in the bottom right-hand corner. 4 actuators. The actuators working in synchronized mode. So each pair of actuators is applying a symmetrical deformation. So the center of the specimen stays in the center of the machine. And we've supplied machines like that with RF heating for metallic specimens, things like confocal microscopes, which look at the center of the specimen. And again, because the center of the specimen is stationary, you can actually do things like imaging and look in detail at crack growth, which is kind of a very powerful feature of a machine like that. Okay, I'll move on to 4-point bend testing of composites, including composite rods. I'll first say a couple of things about 4-point bend testing. Well, one thing to say is that a 4-point bend configuration is actually overdetermined, so it's overconstrained, and that it requires an accurate specimen. If all the anvils are to contact the specimen with at the same time, with the same pressure. Excuse me, I need a quick sip of water here. So you see an example there in the drawing of a 3-point fixture. It's like a 3-point spool. It will always make contact with the specimen, no matter what the specimen shape is. That's not true of the 4-point configuration. You see there's actually one anvil is in contact, but the other anvil there's actually a gap. The way that those kinds of things, and of course there's also the other direction of orthogonal to the screen here. And the way this is resolved in things like sandwich core and concrete testing is that the anvils are actually made to articulate. So the anvils will rotate and will find the correct position on the specimen. That's not generally done for laminate testing. Another thing is that for 4-point bend fixtures, that we need to 4-point bend configuration, we need to measure the center point deflection. It's no good looking at the machine deflection because that is not equal to the deflection in the center of the specimen. So we need some kind of deflection measurement, and you see that in the photograph there. It's actually an extensometer attached to a plunger, measuring the deflection of the center of the specimen. And we would need that to calculate the specimen strains. So, are there any specific issues with the testing of composite rods? And I'm assuming here we're talking about unidirectional pultruded type materials. In this case, you obviously got a small contact area between the flat anvils of the fixture and the round rods, because it's a cylinder connected to a flat here, so it's point contact. There's going to be high stresses at the point contact. and that will probably lead to some kind of crushing of the material, especially as UD material tends not to be very strong in the transverse direction anyway. So that might cause premature failure. Failure itself is going to probably ultimately be due to either compression or shear, because these materials, whereas they're very strong in axial tension, not particularly strong in compression or shear. Okay, so I think.
Yeah, I got a question here. 3-point versus 4-point bend fixture, which is better, and why would you choose one versus the other?
Okay. Well, in general, the 4-point is usually the better choice, because with the 4-point you have got this area with a constant bending moment between the center two angles, so you've got a uniform strain, outer fiber, and strain on the specimen. So you've got a bigger volume of the specimen exposed to that level of stress or strain, or stress and strain, and you haven't got a peak in the in those strains where the upper anvil contact. So 4-point should generally give you more reliable materials data. Okay.
Thanks, Ian.
Okay. So best practice recommendations for tensile lap shear. Oh, expose the food. Right, start again. So lap specimen, simple lap shear adhesive joint here, as described in the 3163. If that is gripped in normal symmetrical grips, a grip which would grip along the center line of the machine, it will cause that specimen to bend, and in particular, it's going to cause significant peeling forces around the joint. Now, those peeling forces can reduce the adhesion, the peak load very significantly. It's much easier to peel something apart than it is to actually pull it apart normally. So you really want to try and avoid those kind of peeling forces. One solution is to pack out the test piece with packing pieces that are as thick as the substrate, and that will get the joint back onto the center line of the test machine. The other solution is to actually offset the grips, and we can do that with several of our different grip types. We have pneumatic grips up to 10 kilonewtons in capacity with adjustable jaw face positions. So those jaw faces can be offset to do this. We also have manual mechanical grips, again, independent adjustment of the jaw faces on either side of the grip. So you can do the offset. And we can also supply special wedge grip inserts for our 100 and 250 kilonewton precision manual wedge grips, which will also allow offsetting of the wedge grip. So that allows us to test very high force lap shear joints in using those grips. Okay, then the best ways to measure strain on components during testing. Well, this slide just highlights all of the different, or most of the different common strain measurement techniques, going from extensometer types, of which there are obviously a wide variety, but extensometer types are not generally going to be suitable for component testing. So in most cases, they're very suitable for coupon testing, not really useful for component testing. For component testing, we're really looking at strain gauges. It's something that we can readily connect to our systems. And in fact, multiple strain gauges can be connected, as you see. There's a single adapter in the photograph, and then a multi-channel add-on to our system, so we could support up to 11 strain gauges on the typical electromechanical testing machine. Then we can move to DIC. DIC being a full field optical technique, which relies on patterning the specimen or the component under test with a random speckle pattern, and then computing from a series of images the deformations. So this will compute the complete deformation field on the component under test, and then that deformation field can be analyzed to produce a complete strain map. So it's a strain map in the sense that we have a full field strain, so covering as much of the specimen components as we would like, and we're also picking up all the different strain components. So we can pick up the axial strain, the transverse strain, the shear strain, the full strain tensor at every point in the image. The nice thing about, in particular, with the DIC package that we offer with our video extensometer is the fact that that's fully integrated with the other data acquisition channels on the testing machine. So you can very easily produce graphs of force versus strain generated from the DIC, which is something. Integration of the different sensor channels is somewhat difficult in some situations. Okay. So best practices for hot wet conditioning of composite coupons. When is it necessary to test under controlled humidity? Okay. Well, typically when you're conditioning composite materials in humid environments, it will take a long time, days, weeks, for these materials to come into equilibrium with the surrounding moisture levels. It's typically work that's typically done in a conditioning chamber. See a typical chamber in the slide. Not something that Instron supplies, not the conditioning chambers. We supply chambers for the testing machines. So it is possible to accelerate that process by using basically an autoclave using heat and pressure. And there's a new ISO standard which is currently being discussed in committee that is going to standardize those techniques of accelerated conditioning. When it comes to actually testing the static properties of a conditioned specimen, it's generally entirely possible to just use a simple heat-cool chamber. There's no need to actually reproduce the humid environment when you're doing the static testing, because the timescales associated with absorbing the moisture are the same as they would be for absorbing it. So the coupons are not going to lose significant amounts of moisture over the duration of the tensile test, even at temperature. On the other hand, if you are actually doing long-term tests, like a creep test or a fatigue test, then it may be necessary to maintain a humid environment on a constant basis. And this can be done with mechanically cooled chambers on the testing machines with humidity and with the appropriate selection of grips, which obviously need to work reliably in the humid environment. And also grips would generally need to be heated so that there isn't an excessive amount of condensation on the grips, which will interfere with the humidity control.
Okay, Ian, I have a question for you on this one.
Sure, yeah.
So regarding the accelerating process, when and why would you choose to do that?
Well, it's a question of productivity, really. If you want results quickly, you're going to you'd rather not wait for the days or weeks that it might take a specimen to come into equilibrium using a conventional approach. So it's that's the reason, yeah, just to speed up the whole process.
Okay, thanks, Ian.
Okay.
I think that's your last slide.
This is the last slide. Yeah, I think we have a few more questions from the audience.
Yes. So thank you for that, Ian. And thank you for everyone's questions coming in. There's as you saw, there's been a lot more than we can probably manage, but I'm going to try and answer some of them now, or go back and forth with Ian. So the first one I would have here is how important is the inclusion of an alignment fixture and software in a composites testing UTM? Is it only for NADCAP?
That's a good question. I mean, I guess the answer would be that, you know, NADCAP include alignment criteria in their checklists for a very good reason, and that is that the alignment ensures reliable, good quality data. So if you want reliable, good quality data, I think you need to pay attention to alignment. And the best way to do that is with an alignment fixture and also with a set of grips which have been shown to grip specimens repeatedly. And you know, and that whole lot to be verified with a strain gauge alignment specimen, following the same kind of rules as would be in the NADCAP checklist, which in fact the ASTM standard for alignment, ASTM 1012, is actually now aligned with the NADCAP checklists. So, you know, if you want an alignment to ASTM, fine. I mean, that's, you know, that's the ASTM alignment standard. It just happens to be the same as NADCAP. Hopefully that's a
good question.
Okay, good question.
Here's a slightly simpler one. Were the grips that you showed in the LN2 chamber hydraulically operated?
Yes, they were. Yeah. Though in the previous image, in the LN2 cool chamber, yes, those are hydraulically actuated grips, but the hydraulics are not inside the chamber. The pistons are actually located outside of the chamber, and then you have two coaxial sleeve and an inner rod that actually are activating the grip head. You need to do that for, you know, in order to have reliable operation. You don't really want to be putting hydraulics inside the chamber.
Then we had a question regarding your the lap shear slides. Could you, offsetting the grips, put a bending force on the load cell?
It could put a small side load into, or offset load into the load cell. I think but all of the Instron load cells are specific. You know, we design and manufacture our own load cells, and they're all specified for this kind of operation. So we have specs for the effect of small offsets on accuracy. And basically, small offsets will not affect the accuracy to any degree, or the reliability of the load cell.
Great. We had another one here, which wasn't covered in the slides, I guess, but to find Poisson's ratio, how can you calculate both the lateral and linear strains at the same time?
Okay, well, the solution to that would be to use I guess the two solutions to that. One would be to use bonded strain gauges, use an axial strain gauge and a transverse strain gauge, or maybe 4 gauge total if you have them on both sides of the specimen for averaging. That would be 4 gauges. So bonding 4 gauges and then conditioning 4 gauges. Or a more convenient solution is to use a biaxial extensometer. So we have a dedicated biaxial extensometer, which is targeted at composite use, and that provides averaging axial measurement and a transverse measurement in a single extensometer, which is easy to attach, and that will give you your strain measurements for Poisson's ratio.
Great, thanks. What strain rates can we do testing using hydraulic machines?
Okay. Well, a sort of depends on the particular hydraulic machine. A typical hydraulic machine is probably capable of maybe speeds of up to something like a meter a second. Fairly lively hydraulic machine, a meter a second. We would be able to supply dedicated high rates of the hydraulic machines, our so-called VHS series, and they are capable of speeds of up to 25 meters per second. So 25 meters per second on a 25 millimeter gauge length would give you a strain rate of 1,000 per second, which is in the kind of, which is going to be the kind of rates that you need for crash simulation on materials.
Great. How to do mechanical, physical, and chemical testing of pre-preg material?
Well, the mechanical testing of pre-preg materials is not, I would say it's not sort of very widespread at the moment, but it may become more important as we move towards more automated handling of materials and robotic assembly. I guess the significant mechanical test on pre-pregs at the moment would be a tack test, where you're actually looking at the stickiness of the pre-preg by actually pressing down on a piece of pre-preg with a known force, a known time, and then actually measuring the force required to actually separate the anvils from that pre-preg, and that's giving this significant this tack parameter, which again is probably not needed if you're doing manual layups of pre-pregs, but once you're doing robotic layups of pre-pregs, robot handling needs to know what these kind of forces are going to be. And I think we might see more development of more mechanical testing for pre-pregs, maybe things like axial strength and the other things as automation becomes more prevalent.
Okay, great, Ian. I think we only got time for a couple more. Sorry for overrunning, everyone. How can we find single fiber mechanical properties?
Okay, well, single fiber mechanical properties, I guess, how do you find the single fiber is the first thing, because these fibers are pretty small. But the fibers are small. It is possible to do single fiber testing on one of our machines. It's a fairly manual process. You would need to isolate the fiber, and then probably bond the fiber to an aperture card, which is a frame to hold the fiber. Glue the fiber to that frame using cyanoacrylate glues or something like that. And then you can put that into a machine with a low force load cell, 5 Newton load cell, say, which would measure down to about 5 millinewtons, and a set of small pneumatic grips. Load the specimen, cut the aperture card, leaving the fiber in place, and then you can do a fiber test. Quite manually intensive, but possible.
Okay, thanks. And I guess this will be the final one. So what is the current state of the art and acceptance in the field of using DIC and non-contacting extensometer for composites?
Well, it's a work in progress, I would say. There is the IDIX, which is the International DIC Society, and ASTM, and organizations in Germany as well, there's a lot of discussion about standardizing DIC at the moment. At the moment, there are no calibration standards that are directly applicable to DIC techniques, and developing them is quite involved because DIC just has so many degrees of freedom it's such a powerful tool, but it measures so many things, and in so many, it's very difficult to actually calibrate that, especially when you go to 3D DIC, where you're actually talking about calibrating a volume in space rather than just a simple sort of 2 points you would get from a conventional extensometer. So yeah, a work in progress. It's not standardized. It will be probably in the next 10 years. It can give good results, and a lot of people are using it and are using it for important, traceable kind of work, but they are coming up with ad hoc calibration solutions rather than being able to go to an off-the-shelf calibration standard or the like. But yeah, definitely a very important and a very busy field right now.
Okay, great. I think that's all the time we have for questions. Apologies if we didn't get to answering yours. We'll aim to reach out with you. And thank you very much, Ian.
Okay. Thank you, everyone.
All right, yeah, thanks, Matt. Thanks, Ian. So yeah, that's going to do it for today. Just a few quick notes before we wrap things up. Today's recording will be available on our YouTube channel and just probably by tomorrow. I know a few of you also asked for the slide deck, so I'll work with Ian to make sure we can get a copy of that sent out with the recording. And then next week, we're going to be joined by Landon Goldfarb. He's one of our senior application engineers. He's going to be discussing injectable drug delivery devices with tips for testing these devices in compliance with international standards. There's a link on Instron.com if you want to sign up for that one. So with that said, I just want to thank Ian for coming back for today's webinar. Matt, thanks for handling all of the questions. I know there were so many good ones. It's tough to pick which ones that we covered today. And thank all of you for attending and for sending us your questions. This was really great. So stay healthy, everyone. We hope to see you again next time.